Okay, here we have some more practice with Gauss's law and conductors. In this case here, it looks like we do have spheres, and we have a solid sphere in the center, and then a spherical shell outside of that. And the question is, what is the surface charge density on the inner surface of the outer shell? So that's right here, and I don't know if it's going to be positive or negative, but the idea is what charges, either positive or negative, are induced on this inner shell because of the charge inside on the sphere inside there. And so, again, this is solved with Gauss's law. We use it all the time, and the big idea is that we know, since we have a conductor here on the outside, we know that anywhere in this conductor, as I draw a circle around here, E is equal to 0. The electric field must be 0. And so I can apply Gauss's law around there, and I can see that the integral of E dot dA here is Q enclosed over epsilon naught. And that's going to be 0 because E equals 0. So that means my total charge enclosed must be equal to 0. So my total charge enclosed must be 0. Well, I know that I have Q1 for sure enclosed, right? Because that's in the inner, the solid conductor there. And so then the other part I have is whatever charge is on this inner surface. So let me just write that out. So the charge enclosed is going to be the charge on the inner sphere plus the charge on the inner surface, and that's the one I'm trying to find out. So we know the charge on that inner surface must be minus Q, and to turn that into a charge density, we'll have to figure out how much area that charge is distributed over, and so that's going to be the surface area of the inner side of that sphere, which is going to be 4 pi r squared, or in this case 4 pi b squared.